Welcome to Chapter 4, the final chapter of our Spintronics Introduction series. In this chapter, we'll explore how the physics we've learned translates into real-world technology. From hard disk drives that store your data, to MRAM that could revolutionize computing, to cutting-edge quantum applications, Spintronics is already changing our world and promises even more for the future. We'll cover 5 main application areas. Hard disk drive read heads were the first major commercial success. MRAM technology is now entering mainstream use. Spin-orbit torque devices represent the next generation. Quantum applications connect Spintronics with quantum computing, and will survey exciting future research directions. Let's see how Spintronics is making an impact. The hard disk drive read head was the first mass-market Spintronics application, and the one that turned the field into a multi-billion-dollar industry. It's a remarkable success story of how fundamental physics research transformed into ubiquitous technology within just a decade of the GMR discovery. The timeline shows dramatic progress. In 1991, AMR heads supported about 1 gigabit per square inch. IBM introduced GMR heads in 1997, immediately pushing density to 10 gigabits. TMR heads in 2004 reached 100 gigabits. Advanced techniques like SMR and HAMR now enable over 1 terabit per square inch. That's a 100-fold improvement since GMR heads arrived in 1997, and a 1,000-fold since the AMR era, directly enabled by Spintronics. A GMR read head uses the spin valve structure we studied. The free layer is thin and magnetically soft, responding to stray fields from recorded bits. The spacer is non-magnetic copper. The pinned layer has fixed magnetization set by an antiferromagnetic layer. When a magnetic bit passes below, it rotates the free layer magnetization, changing resistance. This resistance change is converted to a voltage signal that reads the data. This log-scale plot shows the exponential growth in storage density. Each technology transition, marked on the graph, enabled continued scaling. AMR reached its limits in the mid-1990s. GMR extended the trend for another decade. TMR provided the next leap. Today's drives use advanced techniques like shingled magnetic recording and heat-assisted magnetic recording. All rely on the magnetoresistance sensing that Spintronics enables. MRAM, or magnetoresistance random access memory, uses MTJ cells as storage elements. It combines the non-volatility of flash with the speed of SRAM, potentially offering the best of both worlds. 3 generations of MRAM have evolved. Toggle MRAM used magnetic field writing and was the first commercial product, but had high power consumption. STT MRAM uses spin transfer torque and is now mainstream, offering good density and performance. SOT-MRAM uses spin-orbit torque and promises even faster switching and better endurance. Each generation improves on the previous by using more efficient spin manipulation techniques. In STT-MRAM, current flows through the MTJ itself. When spin-polarized electrons from the pinned layer reach the free layer, they transfer spin angular momentum. If the current exceeds a critical value, this torque overcomes damping and switches the free layer magnetization. The direction of current flow determines whether we write as 0 or 1. This eliminates the need for field-generating lines, enabling high density. Comparing memory technologies reveals MRAM's advantages. Unlike SRAM and DRAM, MRAM is non-volatile, retaining data without power. Unlike flash, MRAM is fast with nanosecond access and has essentially unlimited endurance, over 10 to the 15 write cycles versus 100,000 for flash. This combination makes MRAM attractive for applications from embedded systems to data centers, wherever non-volatility and speed are both needed. Spin-orbit torque devices represent the cutting edge of Spintronics. By using the spin Hall effect we learned about, they offer faster switching and better reliability than STT devices. SOT-MRAM has 3 key advantages over STT-MRAM. First, the read and write current paths are separate, Right current flows through the heavy metal layer, not the MTJ, preventing tunnel barrier degradation and extending lifetime. Second, switching can be sub-nanosecond, faster than STT. Third, lower critical current density reduces power consumption. These advantages make SOTMRAM promising for cache memory applications. The switching current density depends on several factors. Higher magnetic anisotropy requires more current, but larger spin Hall angle reduces the required current. The graph shows how platinum at 8% spin Hall angle requires higher current than beta tungsten at 33%. Topological insulators with spin Hall angles approaching 50% could enable ultra-low power SOT devices. Spintronics connects naturally to quantum computing through spin qubits. Using individual electron spins as quantum bits leverages all the spin physics we've learned in a quantum information context. Three main platforms exist for spin qubits. Semiconductor quantum dots trap single electrons in silicon or gallium arsenide, using their spins as qubits. NV centers in diamond use nitrogen vacancy defect spins and remarkably work at room temperature. Topological approaches using Majorana modes in superconductor ferromagnet structures are predicted to offer inherent protection against errors, though they remain unproven experimentally. Each platform has trade-offs in coherence time, operating temperature, and scalability. Coherence time T2 measures how long quantum information survives. Gauss quantum dots have about 200 microseconds. Silicon quantum dots are much better at 28 milliseconds. NV centers achieve 2 milliseconds at room temperature, which is remarkable. Phosphorus donors in silicon reach about 600 milliseconds, the longest solid-state electron spin coherence measured, though still well short of trapped ions. Longer coherence enables more quantum operations before information is lost. The field of spintronics continues to evolve rapidly. New materials, novel device concepts, fundamental discoveries, and quantum applications are all active research areas promising exciting developments ahead. 4 particularly hot topics deserve mention. Two-dimensional magnets like chromium triiodide and iron germanium telluride show magnetism in atomic layer materials. Skyamians are topologically protected spin textures that can be driven by ultra-low currents. Antiferromagnetic spintronics exploits terahertz dynamics and zero stray fields. Magnonics uses spin waves instead of electron flow for information transfer. Each could enable new device paradigms. Let's look back at our journey through spintronics. Chapter 1 introduced electron spin and the historic GMR discovery. Chapter 2 covered the physics of GMR, TMR, spin injection, and the spin Hall effect. Chapter 3 gave us Python tools to simulate these phenomena, and Chapter 4 showed real applications from hard drives to quantum computing. You now have a solid foundation in this exciting field. To continue learning, intermediate series on spin-orbit interaction and SDT theory are planned. Advanced topics will cover topological spintronics and skyamian physics. The related superconductivity introduction series connects to quantum technology applications. Key review papers by Hirohata, Batty, and Manchan provide deeper technical details. The field continues advancing rapidly, so keep exploring. Congratulations on completing the Spintronics Introduction series. You've learned fundamental concepts from electron spin to quantum applications. From the 1988 GMR discovery to today's MRAM products and tomorrow's quantum computers, Spintronics continues transforming electronics. Thank you for learning with us at AI Terakoya. We hope this knowledge serves you well in your studies and research.